Welcome to Material Science 303. My name is Armin Rahmani. I'll be the instructor of this course this quarter. So, as you know, this is a one-credit class for material science minors who are not physics majors. And the main purpose of the course is an introduction to the quantum mechanics and a little bit of statistical mechanics toward the end. So quantum mechanics is a framework that allows us to understand basically all materials. So starting from atoms and molecules and electrons, they're all governed by the laws of quantum mechanics, and materials are a big collection of these particles, and they all interact with one another, but basically the same basic laws of quantum mechanics give rise to various properties of materials. So something is a metal, for example, it conducts heat and electricity very well. There's a crystal that's transparent, it lets light pass through. Metals are reflective. There are other materials which absorb a lot of light. Then different materials have different electronic properties, can have various states of matter, superconductors, superfluids, semiconductors. So all of these fascinating phenomena, and basically all of chemistry, if you go down to the very basic fundamental laws that give rise to these phenomena, they're not the laws of classical mechanics. So it was understood in the 20th century that classical mechanics and classical electromagnetism are not enough to explain physics. So historically, quantum mechanics was developed because there were a lot of inconsistencies between experimental predictions based on classical physics, theoretical predictions based on classical physics, and experimental observations. So this really gave rise to a revolution in physics. At the same time, special theory of relativity was discovered by Einstein, so that was a separate revolution, both happening toward the beginning of the last century. So in this course, we will mainly try to gain an understanding, a very basic understanding of quantum physics. Of course, this is a one-credit class, so we can't go into too much detail, and we can't cover a broad range of materials. But I think it's going to be a very interesting introduction to get some intuition about the really counterintuitive principles that govern the world around us. We'll try to get some practice with problem solving, so it's not really like a kind of a popular science survey course from a distance. It is for science majors, and we will try to, for the materials that we cover, we will try to, gain some practice, go into a little bit of depth, time permitting. So there is no required textbook for the course, but a textbook that's really useful and I highly recommend if you want to go into more depth and detail is A Modern Physics by Randy Harris. So this is a standard textbook in the physics department for the two modern physics courses, Modern Physics 1 and 2. These are 2 3-credit courses, so which cover a good chunk of the book. We will be covering, of course, a small part of this book. So yeah, I'll pick and choose some topics from the book. So in the syllabus, the chapters that we will talk about are mentioned. So first, we start by talking about, let's see, some of the experimental foundations and the principles of quantum mechanics. So primarily we'll mention a couple of experiments and mainly talk about the phenomenon of wave-particle duality. The fact that things that we think of as particles, like electrons, can exhibit behavior that's associated with waves. And things that we previously thought about as waves, like light, can exhibit behavior that we associate with particles. And then this begs the question, okay, so what is this wave when we think about things like electrons? So that leads to thinking about the probabilistic nature of matter. It turns out that the behavior of matter is not deterministic. Like when you go to those scales, those small scales of electrons and atoms, the result of an experimental observation for a given system is not predetermined. There's an inherent probabilistic nature to it. So yeah, we'll talk about the probabilistic nature of matter, and then we'll introduce a key quantity known as the wave function, which is kind of a mathematical object that when you square it, it tells us about the probability of finding a particle somewhere in a measurement. And then we'll introduce, so this first part, we'll pick some sections from chapters 3 and 4 of the book. Then we move on to chapter 5. We introduce the Schrodinger equation, which is a fundamental law of nature that governs the behavior of this wave function. And then we'll do a couple of applications. We'll do two examples in one dimension. The particle in an infinite box confined in an infinite potential, and then a simple harmonic oscillator. We'll talk about the quantum mechanical treatment of the simple harmonic oscillator. Then we'll do a three-dimensional example. Again, the most famous example is the hydrogen atom. One of the first triumphs of quantum mechanics was explaining the spectrum of light emitted from atoms, in particular the hydrogen atom. And then toward the end, we touch upon statistical mechanics and talk about classical and quantum statistical mechanical distributions. So StatMech is primarily from chapter 9, and hydrogen atom is discussed in chapter 7 of the book. So that's a list of topics that we'll be talking about in this very short 1-credit introduction. As far as structure, there's no exam, so there are weekly classes, which means I'll post one lecture per week, and there's going to be a short homework, typically one problem, which may have different parts that you'll work on. And homework is basically the entire grade, so the grade is entirely based 100% on the homework. I'll have office hours via Zoom, so those are on Mondays at 11 a.m. and I'll create some links on Canvas, which you can just click on and go to the Zoom meeting. And if you can't make to that time, you have a question, or there's something that you want to discuss privately, because in these office hours, of course, all students can come in, right? So questions about homework, about lecture, about something you read in the book are perfect. But if there's some private matter that you want to discuss with me, just send an email and we'll arrange a separate meeting. All right, so let's get started talking about some of the experimental inconsistencies that gave rise to the discovery of quantum mechanics. So there were several. There was a phenomenon known as the Blackbody Radiation. So we won't talk about it that much, but it was historically the first, and Max Planck was the one who made sense of it by kind of making the assumption that energy comes in chunks, known as quanta. So that's kind of the origin of the word quantum mechanics. Another one was the photoelectric effect. So today I'll spend a little bit of time going into some depth discussing the photoelectric effect. It's again like you shine light on some material, typically a piece of metal, and the light has energy, so it can kick out electrons from this metal. And there were some experimental observations about the energy of these electrons that get kicked out and how that depends on the frequency of the light and the energy or the intensity of the light. So it turns out that what was observed was in direct contradiction to what you would predict based on Maxwell's theory of electromagnetism, treating light as a wave of electric and magnetic fields propagating in space and interacting with electrons through just the simple laws of electromagnetism. So that led Einstein to conjecture that, well, maybe light comes also in chunks. Of course, that's a very revolutionary idea, because there's a huge body, or there was, and there is, of experimental observations where light does behave like wave. I mean, we studied in Physics 163 things like the double slit interference. We see these fringes that are formed. They can be explained by treating light as a wave that propagates, and it works beautifully. So it's not that, oh, light was a wave and now is a particle. It's like there are circumstances where it behaves like a wave. You can explain the observation by treating it as a wave, and there are circumstances where you should treat it like particles, like chunks of energy. And that's the fundamental duality that really lies somehow at the foundation of quantum physics. And then, of course, there were further developments where people discovered that things that were thought of as particles, like electrons, for most intents and purposes, they're just particles localized in space. You know, you detect an electron, it hits the screen and you see a point, or maybe it's moving and it forms a line. So very nice, like a very small particle. But then there were phenomena that, were very much wave-like. You could see interference fringes in the pattern formed by electrons hitting a screen. So before going into more detail, let's just review a little bit about what the experiment on the photoelectric effect was and what was observed, in fact. All right, so let's talk about the photoelectric effect. So this is from section 3.2 of Harris. So basically the photoelectric effect is you have a piece of material, maybe a metal or something like that, and then you shine light on it. And as you shine light on this material, electrons get emitted from it, so they get kicked out of this material. So let's say you have an electron here that gets kicked out. And then these electrons are moving away. They just got kicked out of the material, so they have some kinetic energy, right? They're massive particles that are moving. So, at least classically, like 1/2 mv squared, they have some kinetic energy that's somehow coming from the light. So suppose experimentally I want to measure the kinetic energy of the electron, at least the maximum kinetic energy. I mean, there could be a distribution, right? Not all of them have identical kinetic energy. But suppose I want to find the maximum, the largest kinetic energy that an electron emitted from the material due to shining light on it has. So the experiment is quite clever. The experiment that was done goes like this. So suppose I put another plate on this side, right? And then this electron kind of goes, hits the other plate, gets collected there. So if you now construct a circuit, you create a path, then electron is negatively charged. So there's going to be negative charge moving this way as it gets absorbed by this. And if you put an ammeter here, let's say, you're going to measure a current I moving this way, right? These negative charged particles are emitted because of the light. They go hit the other plate, and then here you have some negative charge. Here you've lost negative charge, so they move this way, and we can read some current. Okay. Now, how do we relate that to the maximum kinetic energy of the electron? Well, the trick is you can balance it with something else. So suppose let me draw this again. I now put a battery with adjustable voltage in my circuit. So here is this electrode. Here is again the light. And without anything, there seems to be some current this way, right? So suppose I want to put a battery that sends current in the opposite direction, right? So what it does is that it creates an electric field going this way between the two electrodes. Now, as you increase the voltage, you increase that electric field, that in turn slows down these electrons that are emitted from this electrode as they travel this way. This electric field exerts a force to the left on them. It slows them down. And if you make that voltage large enough, there's going to be a point where these electrons don't reach the other plate, and the current goes to zero. Right? So as I increase my voltage here, this is an adjustable voltage. As I increase it, my current goes down and ultimately it reaches zero. So let's say V stop is the voltage for which I is zero. Very simple circuit. You just make that material that's emitting electrons kind of a plate of a capacitor, and you put adjustable voltage, you measure current, you see when it goes to zero, and then that gives you this V stop voltage, the voltage that's large enough which stops the electron, which has some kinetic energy K here from reaching the other plate. Well, then the relationship is really simple. So the kinetic energy of the electron, at least the maximum kinetic energy, is going to be just V stop times E, right? Voltage, potential, was energy divided by charge. Just to remind you a little bit about the mechanics of how this works, remember from E and M, this electric field, if the distance between the two electrodes is d, will be voltage divided by the distance. Right. And then it's the electric field times charge is the force. So force times distance is work done, and that work, which is equal to, so let's say force is E times the charge, and then there's going to be some work done on the electron. At least its magnitude is force times distance, which is E, the electric field, E times D, and E times D is just V. So the work, if the work done is equal to the kinetic energy, then the kinetic energy here can go to 0, and then that kills the current. This electron is slowed down as it travels between the plates, and if the voltage is big enough, it's not going to reach there. So experimentally, by kind of a very simple circuit design, we can measure the kinetic energy, or the maximum kinetic energy of electrons emitted from this piece of metal. Okay, fine. So what do we expect this kinetic energy to depend on? Well, let's think of light as electromagnetic radiation, electromagnetic waves. So remember, light intensity not to be confused with the current, so let me not call it I, just call it intensity, is proportional to the electric field of the light wave. So let's call it, something like this. Suppose there's some electric field here. Again, not the electric field due to the battery between the plates, the electric field of the actual light wave. So let's call that E light squared. Okay, so the brighter your light is, the more energy it has per volume. It has larger electric fields, and then if these electric fields are what will move the electrons and kick them out of the material, well, our classical physics says, well, what should happen is that if you have a light with higher intensity, your electrons should have a higher energy, right? These electrons that get kicked out of this piece of material should be more energetic, should have a higher kinetic energy. That doesn't happen. So that was one of the big mysteries of the photoelectric effect. You increase the intensity of the light. Suppose you have like one of these lasers. You put 10 of them next to each other. You have 10 times the intensity. You don't increase the kinetic energy of the individual electrons that get kicked out. You would kick out more electrons. You would increase the number of electrons that get kicked out. But their kinetic energy is independent of the intensity. So observation is that this Ke max kinetic energy is independent of intensity. And that's a real contradiction, right? So if you have this light, this electromagnetic wave kind of entering the material, the electric field of the light is exerting some force on the electron. So in this classical picture, if you double that electric field, you double the forces. You should do kind of double work. You should double the kinetic energy as you kick it out. So, well, at least at least increase it, because there's probably some fixed energy that you need to spend to kind of remove the electron from the material. It's being attracted by the material, by, let's say, the ions in the material. But there's going to be some energy you spend that's fixed, and then as you increase the intensity, one expects to increase the kinetic energy, and that doesn't happen. So that was a clear contradiction with classical, kind of with the interpretation of light as just a simple electromagnetic wave. Furthermore, if you change the frequency of the light, again, the frequency, it tells us like how many ups and downs we have per time. So you kind of move up and down. How fast is that changing? Change the frequency of light. Classically, we don't expect it to have much of an effect on the kinetic energy. But it turns out that experimentally, it does. So again, assume you have this light source. You can change its frequency. So let's say F is the frequency and you can remember from 163 that frequency basically has to do with the color of light, right? You go from blue light, which is high frequency, to red light, which is lower frequency, for example. You change so let's say F is the frequency of light. Let me plot this maximum kinetic energy that we can measure using this experimental setup as a function of the frequency. Well, what we see is quite interesting. Up to some frequency, the kinetic energy is 0. So electrons basically don't get emitted. After a certain frequency, the kinetic energy goes up. So let's say you have some data point, something like this, and it's pretty much linear with the frequency. So that's again another very strange observation that one cannot explain using classical electromagnetism, just treating light as a wave of electric and magnetic field just governed by Maxwell's equations. So Einstein in 1905, one of the important papers he wrote in that year was the paper on the photoelectric effect. So he said, well, these are the experimental facts. How can we make sense of them? Well, the conjecture is, what if light comes in chunks? Or particles? Some localized chunk of energy, HF. H is the Planck constant, which was introduced in the context of blackbody radiation. But let's not worry about that. Let's say light comes in some chunks, in some packets, whose energy is proportional to the frequency. Then the intensity, as you increase the intensity, you just increase the number of these packets. You have more of these particles of light. So then it makes sense that the kinetic energy of the individual electrons that are emitted are going to be independent of the intensity, right? You just increase the number of these packets. These packets hit the material. Each of them will kick out maybe an electron. So as you increase the number of packets or increase the intensity, you just increase the number of electrons that get kicked out rather than the kinetic energy of the individual electrons that get kicked out. Furthermore, it just explains this, right? Because suppose there's some constant energy to remove an electron from the material. It's bound in there, right? And you need to spend a certain amount of energy to remove it. So let's say we introduce something called the work function, which is a property of the material. And it's just energy needed to, let's say, unbound an electron. Let's call that to be phi, give it a name. So then what happens? See, as we increase F, as long as H times F is smaller than phi, then we cannot remove the electron. So that justifies this. So this is going to be phi over H, right? At this frequency, H times the frequency is phi. And as if you have a lower frequency, your packets have a smaller energy than the energy needed to kind of pull away this electron from the material. So you can't kick it out, and the kinetic energy is 0. And then once you increase the frequency further, well, the extra energy just translates to the kinetic energy of the electron. So we end up with this important equation using this picture. And that agrees with the experimental observation. So the photoelectric effect was a phenomenon where you couldn't really explain it with treating light as a wave, as an electromagnetic wave. And we could quite easily, as Einstein did, explain it by saying, well, maybe light behaves like a particle. And these particles have the special property that their energy is proportional to the frequency of light. Okay, so that was one observation which gave rise to this concept of duality, right? Light is sometimes, when you see, for example, fringes in a double slit interference experiment, behaves very much like a wave. Everything is fine. And there are phenomena where we can't explain them without kind of treating light as a particle. And then what does that even mean? Like, it's really a daring equation to write, because frequency is a property of a wave, right? And then we're saying there are these packages, these particles, whose energy is proportional to something that's a property of a wave that's not a particle, right? You see there's this distinction in our classical intuition that, well, a particle is something localized in space. It's a piece of sand or a rock or some object that's localized in space. And a wave is like some disturbance that extended in space and time, and there's periodicity. There's temporal periodicity that's determined by the frequency. Like if you look at one point in space, how fast is this thing oscillating? So that's the frequency. There's kind of the speed of propagation. So it's a very different creature fundamentally. And the frequency is really a property that we made sense of when we were thinking about waves, some extended phenomenon in time and space with oscillatory propagating behavior. The particle is just something that's localized somewhere in space, and it can move in space in some manner. So somehow it's really thinking, it's embracing the contradiction, saying, well, let's suppose it's a particle, and that particle has kinetic energy that's proportional to a property, to another property. that's associated with the wave-like nature of light. Note that, I mean, this laser that you shine and you observe throughout the whole thing, of course, that light has some color, right? So the frequency is there in some way. But the challenge is really to recognize this. So I think this was a very very nice discovery for the dual nature of matter, for the wave particle duality. So then there was a very important insight in physics due to a French physicist called Louis de Broglie. Probably the better pronunciation is de Broglie or something like that. Who was really fascinated by Einstein's theory of the photoelectric effect. It's like, okay, so we have light. We know it shows interference fringes. We know it has diffraction. We've understood it very well as a wave. And then now here's this experiment, which, you can only explain it by kind of admitting that light is like a particle, comes in chunks. So what if there's like some kind of symmetry in nature? What if the things that we thought were particles, like an electron, maybe there's something wave-like associated with them? It's a very interesting insight. And then he pushed it a little bit further. So he said, well, see, this equation relates, something particle-like, the kinetic energy of a particle, to something wave-like, like its frequency. So can we do more? Can we, if we have particles with some energy and some momentum, can we associate these wave-type characteristics to them? And the interpretation then, of course, needs to be discovered. But how can we do that? Well, there are a couple of things, right? So let's say we say energy from the photoelectric effect is H times F, right? Because if that's the kinetic energy of the electron that gets kicked out, well, this is the kinetic energy of this chunk of light, and the name for it is photon. This chunk of light is called photon. So HF is the energy of a photon, and then this energy phi is spent to just remove the binding between the electron and the material, and the rest goes into the kinetic energy of the electron. So generally for a photon, if Einstein is right, we have an energy that's just H times F. So maybe that's also true for particles. So maybe in general, energy can be associated with frequency. Okay, so that's interesting. But what else can we say? So again, de Broglie knew about Einstein's theory of relativity, and in relativity, energy in general is given by c squared p squared plus mass c squared quantity squared. So that's a result from the special theory of relativity, where this is energy, this is speed of light, a constant of nature, this is momentum, this is mass. For a photon, we know that light doesn't have mass. It's not massive. So m is 0. So relativity predicts that E is just, you take the square root of c squared p squared, it's just Cp, the speed of light times the momentum. So if you carry this line of thought forward, you can also say, well, maybe Cp is hf. So maybe we can somehow relate the momentum of a particle to frequency, or associate the frequency to momentum. Furthermore, we know from the theory of waves that, there are two kinds of oscillations in a wave, right? There's temporal oscillations, oscillations in time if you fix the space, and those have to do with the frequency, how fast you move up and down as a function of time. And then there's spatial oscillations, which have to do with the wavelength, right? How extended, if you just take a snapshot of your wave, what is the periodicity of the pattern that you see in space? And we know those are related, so you've seen these in 163. We know that lambda f for any wave in general is equal to the speed of propagation. So if I put these together, I can write Cp is h, and instead of f I write c over lambda. So that gives p becomes, if I cancel out the c's from two sides, becomes h over lambda. Right, so from here, just, I hope I'm not too quick, from here you have f is c over lambda. Let's divide the two sides by lambda. And basically now I'm taking this, inserting it into here. So Cp becomes h times f, and for f I put c over lambda. Then I cancel out the c's, I find p is h over lambda. And then I can write lambda in terms of h and p. So you can write lambda is p over, h over p. Erase. So that's a remarkable relationship, right? So now it works for photons, right? Everything we did works for photons. It's basically by taking two discoveries of Einstein. One, kind of the relationship between energy and momentum, and just applying it to the photon with mass equals 0. And then taking this kind of conjecture that the energy of light particles is h times f, and from it finding that the momentum of light particles is h over lambda, the wavelength of the light, by just using the basic relationship that holds for all waves, in particular light, that relates wavelength, frequency, and the speed of propagation. So we find that for light, lambda is just h over p. Now, you can take this bold step and say maybe for all particles that's true. That's a simple relationship. So maybe all particles of momentum p, there's somehow some wavelength associated with them. We still don't know what that is or what the wave-like behavior is. But that wave-like behavior, if it has some characteristic wavelength, and if it's the same story as light, well, that wavelength should be h, the Planck constant, divided by the momentum. So this is known as the Broglie or the Broglie wavelength. Another relationship is just the relationship between energy and frequency. So again, if that relationship that we found for photons kind of works for other particles, then we expect that the frequency associated with the particle is just its energy divided by h. So saying F is E over H. Right, so this is kind of a remarkable relationship. Still, it seems like just a wild guess, right? At this point, we don't know what that wave associated with particles of matter is, but its two salient characteristics, namely the frequency and the wavelength, the Broglie conjectured that they're related to energy and momentum like that. And the Planck constant appears in both of these relationships. Okay, so let me just summarize some of the things with it. So, see, one can ask, well, seems there's some cheating, right? If you think of this as a derivation, this is basically done for light, and light has mass 0, so it has this relationship where energy is just Cp. That clearly doesn't hold for particles of matter. For an electron, we don't have energy is Cp. Energy is this, and mass of electron is the mass of electron. But somehow you can eliminate mass, if you wish. So it's really a guess. These relationships look very simple. They seem to relate momentum and energy to wavelength and frequency, and only H appears in them. They work for light, so maybe they work for other particles. So this should not be thought of as a derivation, right? It's really a process of discovery based on guessing things. So that's the work of the Broglie, which is quite influential. So this topic that we've been talking about after describing the photoelectric effect is really the beginning of the wave particle duality, right? So the idea is that the wave-like nature of stuff have associated with them wavelength and frequency, and particles, we associate with them energy, right, as they're moving, and momentum. So first let me write the momentum, then the energy. And if there is a duality, so sometimes things behave like particles, sometimes they behave like waves, there is a fundamental relationship that seems to work for light. And de Broglie's conjecture was that, well, maybe it works for other particles. We just need to discover what that wave is, where they behave like waves, and what are those wavelengths and frequencies. And the relationship is as follows, right? So we can relate them using H. So P becomes, let's say, H over lambda. E is H times F. Lambda is H over P. And F is E over H. So next time we'll talk about an experiment, a double slit experiment for electrons, where we can see this duality, and we'll try to verify if, these relationships can lead to something that can be measured experimentally. They somehow correspond to some experimental reality, and then it motivates introducing the notion of a wave function. All right, so that's a good place to stop the first lecture.